I think we have 3 more minutes, so we can wait. So it feels good to be back on campus, I believe. Lots of students are around campus now. You can pick one of those. That one. And don't have that. You have this? Yeah. You can also pick this one.
When will you post us and
Where is this
videos?
I will. I do lag a little bit. Okay, so those are finished, but now you can share. It's fine. You will have to share. Huh?
Is there any sheet left?
Oh, there is no sheet left. Why don't you please share with one of the students? So it's the second class. I was not sure how many students actually show up. Probably I should have brought more of these. That's not good. Probably I can give you one of my sheets. 10:39. Okay, great. Well, okay. It's not a problem. In fact, I can give you one of my sheets. Just try to share. Okay. We don't have any online students. What happened? I don't know. I think it's the right link. Anyways, it's being recorded. So in any case, I will post the recording, which I could not last time. Okay. Welcome everyone. What we will do is we will continue with the same problem. This time around, you have that problem in front of you as well. So for those of you who cannot see a page, just have a look at this problem. This is our problem. And last time, if you remember, instead of having all of these fancy things, I just showed you simple two rods, right? So that's the same problem, but with an extra layer of complexity. What we will do is we will actually write down the answers from the previous class. Okay. So what were those answers? I think 50 kilonewton, if someone can double check. 50 kilonewton. So I think we saw that if we remove this pin, we got 50 kilonewton here. And I urge you to double check with your notes, okay? 50 kilonewton. I will write down the word 50. Right. And similarly here, towards the right hand side, I saw that if I remove the pin, I am getting an answer of, can anyone look at their notes? What was the answer? 40? 40, right? Okay. Now, just one thing before I proceed, because all of you are wondering, why on earth have we made this problem complicated? I will get to that. But before I proceed, I have to tell you one very important thing. Pointer, where is the pointer? Yeah, you see this 50 kilonewton. What you have to understand is that when you remove this pin, and I saw that there is a 50 kilonewton load. I was super happy. I made this arrow. Just make one more arrow, okay? This time around, the direction of the arrow will be like this. What does that mean? It means that this particular bar that I am talking about, it is in, huh? Exactly, tension or extension, tension. Tension is the right word. And similarly, I will draw a yellow arrow one more time, this time around towards the left. And I will say compression is the right word. Excellent. You know what? You can use mine. No. I think I have the notes. So this one is in. So this next time I will bring more copies. So this fellow is in. You know, the hardest part in this problem is to find the pointer actually. Where is the pointer? Yeah, here it is. So it is compression. Let me write down for you. Compression and tension. Now, just imagine if in the start of the problem I had told you that there is a 30 kilonewton load that is hanging and that top bar is in tension and this bar is in compression. You would have asked me, how on earth have you reached to that conclusion? But now you have a feeling of it. So just remember that you removed the pin joint C, you put the reactions, you got the force. You said that the force is in that direction. That's fine. But you don't stop there, okay? You put a yellow arrow there, but opposite to that, you put another yellow arrow. And then you say that this bar is in tension. So far, so good. Right? Makes sense, right? So you are using the statics principles. You are telling me that that bar is in tension and this bar is in compression. Now the problem starts for our 206. Okay, so now you have to use calculators a lot. Let's get going. You will be telling me the answers, please. Quickly. So for those of you who do not have the sheet and cannot see these millimeters, you have to ask me and I can repeat because millimeters are, the dimensions are very small. First thing first, please. First thing first. Probably you want to sit with one of the students who has the sheet. Okay, so first thing first, why don't you all help me with the, where is the 50 kilonewton? The bar BC. Help me with the stress in bar BC. And you will see how the whole problem will keep on getting complicated. Normal stress will be force per unit area. Okay, now force is equal to 50 kilonewtons. What happened? Everything is fine. 50 multiplied by 1000. Then there is a Newton. Then there is area. Okay, what is the area? Now, you have to be careful here. The bar that you see at the bottom, that is flat. You can have a look at the top view as well. But I'm talking about the bar that is at an angle. That one is definitely circular, okay? So in a problem statement, you will be clearly identified that that's a circular bar. So what will be the cross-sectional area? Yes, this is a dia of 20 millimeter. So I think, as one of the students said, it will be A is equal to pi d square by 4, okay? With a d in 20 by 1000. Okay, now you substitute this fellow here, and why don't you all give me an answer, okay? And this fellow will be in meter square. So I will have a beautiful stress in okay, I understand. Actually, you are telling me the area. Yes, yes, sir. No, give me the final stress value. 1.59. You have to give me the answer in pascals or megapascals. 159 megapascal. 1.59, 159 megapascal. Huh? So one of the students has told me that it is 159 into 10 power 6 pascals. Okay. Boom. And then 159 megapascals. Got it? Great. Hang on. It's tension or compression. Tension, right? So this is what you will do. Put a nice and beautiful positive tension. Now you know why did I put a positive? Because I knew that this is in tension. That's why. So why don't you make a comment in your notes that whenever the stresses are positive, or you identify them as positive, or you indicate them as positive, that means you're talking about a tensile stress. Okay. Tensile stress. Huh? Look at here. Tensile stress. Tensile stress. And this is negative stress, a compressive stress. So, okay. I will put a little comment here. It's clear, right?
Whenever stresses are positive, what was after that?
So, if a stress is tensile, I will identify it, or I will indicate a positive. Positive means tensile stress, and negative means compressive. Okay. So tensile, for the positive, you can put a little arrow here with the positive. Okay. Okay. Now, here comes the important piece of the puzzle. If I ask you in this problem, I'm talking about stresses. Should we stop here? Absolutely not. Because you can see here that right now I was focusing here, right? I cannot stop here. You can see that just having a look here, you can see that I don't know from where the structure can break. What is the weakest link? How would I know? It is quite possible that the weakest link in this bar is actually this portion. But where was I focusing on? This portion. I was focusing on this simple portion, and the answer came out to be 159 megapascals. That's fine. Now I have to focus here. So let's focus here, okay? Let's focus here. And for those of you who are wondering, do we know right now whether the structure will break or not? It's too early to comment on that. Right now, we have figured out that there is 159 megapascals of stress in this portion of the rod. Okay, so let me help you with this portion. Why don't you draw a beautiful diagram? So it will be something like this. So there will be a lot of sketching in this course. So please try to draw it on a piece of paper yourself. Then put a beautiful like this. Then, okay. Okay, now it's hard for me. You can do it easily on your piece of paper. Okay, now I will use quickly. Oh, come on. What happened? It's very hard. Anyways, something like this. Okay, and just quick comment. Muhammad Al-Khatabi, Sadiq, and we have Tehshin Chand. Can you just confirm you are hearing me? I don't want the mic to be muted. They are not. Oh, they are. Thank you. Okay, good. Okay, everyone. Now, where is the hole? This is the hole. Yeah, here. Now, you have to imagine there is a force that is going. So imagine force as a liquid that is flowing. Now, that's a far-stretched imagination. But when the force is going, it has to come up with its own path, right? So stress, right now I'm standing here, right? So thinking that right now I am standing here and this portion of the tile or this portion of the floor is not taking any load. That's just ridiculous. When I'm standing here, definitely this fellow is also feeling my load, right? The stress is being distributed. It's very concentrated where I am standing right now. So think it like this, that like something that flows, I have a force that is going through it. And this fellow, nice and beautiful, wants to flow, okay, there is the brush, flows right here, and this fellow wants to go right through here. So it does make sense that this portion of the bar may be the weakest link for me. I have to be careful in the analysis. So why don't you all help me with the with finding stress here? So let's find stresses here. So just to be clear that this is a solid object, I will just make these beautiful lines so you don't get confused. And now I will find the stress with you. So I will put a word C here so you don't lose sight of the fact that I'm focusing here. There is a pin here. I removed it and now I can see a hole here. Now just tell me the stress, please. Stress equal to force divided by area. What is the force? 50 kilonewtons. And I will write 50 multiplied by 1000. Then I will put a capital N for newtons. Then area. Area. Where am I focusing on? Right here. Right here. So tell me the area. No, you have to write it down. It's definitely, I think, available on these sheets, but you don't find that using sheet. You do it yourself. Okay, I will help you. Which area I am looking for? I am looking for this area and this area, right? Because whole is nothing, right? So if I want to see this area, I will say it is, let me think about it. 40, oh, hang on. This total dimension is 40. So let me help you with this. This is 40. And the dia is it 25? I think they are right. This is 25 written. So 40 minus 25 will give me that. So I think area will be 40 minus 25 multiplied by something. Let's find out that something. What is this what is this thickness? So this flat fellow has a thickness of 20. Is it confusing? Is everyone following me? Yes, no, it was a little confusing. So then I will write the word millimeter square. So 40 minus 25 is 15. 20 multiplied by 15 is 300. 300.
You also you got to all don't we have to add pi as well?
Oh no, I will explain this. This is a good question. His question is, should we add pi or not? The answer is that we should not, because probably I should make another drawing to make it clear. It's a good question that why aren't we adding pi? I will explain. Probably this part of the drawing can help you. So I have hole here. I have hole here. And this area is the one that I'm focusing on. So if you can imagine from here, when the force has to go through, it has to go through 20 multiplied by 40 minus 25. How should I explain? So if it's clear, or okay, I will do it one more time. So what I'm trying, I just want another drawing that will be really clear. So probably this drawing will help you. This is the hole. Now force is flowing like this out of the board right into this fellow. Where is the pointer? This fellow, please focus here. Now, if I have to find the area, it will be this and this. So it will be this dimension, which is 20. Please focus here. This is the flat flat portion 20, 20 multiplied by this height, which is 40 minus 25. Minus 25. Is it clear now? So just imagine that the force is flowing right through it.
Why are we calculating stress? Why are we especially focus on the cross-sectional part of the fin and the thinner parts?
No. Oh, your question is why are we focusing at the end, the thinner parts? Or why are we focusing right?
Why are we focusing this cross-sectional area?
Yeah, because just imagine like this. The force is flowing like this. It's flowing through here, going. So it spreads like this. If I can, where is the pointer? Focus here. It goes here. It goes here. So for me, the critical section appears to be right this portion. So that's why I draw a line right here. And that's why I'm focusing on this portion and this portion, because I'm afraid that if the structure has to fail, probably it will fail here. Okay, everyone, why don't you tell me the value, please?
1.67 10 is the power 8.
1.67 into 10 power 8. So from here onwards, I will highly suggest that you give me answers in kPa or MPa. So in megapascals. 167 megapascals. So here comes the answer to our other students as well. Is 167 more or 159? 167. So apparently this surely appears to me the weaker of the two links. If it has to fail, it definitely will fail here. So all this time I was focusing on the circular portion. Turns around that I don't need to worry about that. Okay, everyone. Let's focus on the bar AB quickly. Where is it? This is A. This is B. Oh, there is no space left. That's not good. What should we do now? Give me 1 minute, please. Let's do a control V. Oh, that's nice. I will zoom in again. Okay, so focus. And we have stress equal to, where is stress AB is equal to, just focus on the somewhere in the center of the bar. It was compressive, so minus 40 into 1000 Newton divided by, give me the area. So now look at the top view. Top view shows me that there is it's more like a rectangular section than anything else. So 30 multiplied by 50. Please don't hesitate and let me know if it's not clear. Okay. Answer in megapascals.
27.
Minus 27 appears to be correct. Correct? Okay. Previously, we were getting answers, I think, lower than this. No, higher. Okay, now I am getting minus 26.7, but this is a separate bar, a separate story. Why did I put a negative sign? Because now this is compressive stress. Okay, done. Your book does not talk about it. Probably just for the sake of completeness, if you want, we can discuss this portion as well. Okay, so if you look at from the top view tells you that this bar actually gets divided into this fellow, right? Two of these legs. And all you have to do is, if you have to really focus on the portion with the hole, it will be stress equal to, so you will have 20 into 1000 divided by, and that will be 20 millimeter multiply by this one. You have to help me. Use your imagination. And so think like this, that the force is like this and it goes like this.
Why we said 20 times 1000?
Because you see, this is 20. So this thickness is 20. So when the force has to go here, there will be,
Divided into two parts?
yes, 20 here. And, oh, your question is, why did I put a 20 here?
Ah, yes.
Yes. Because if I remember, this portion had 40. So 20 and 20. That's why I went for it. So 20 multiplied by 50 minus, what is the dia of the hole? 25. Can you please tell me whether it makes sense or not? Think about it. I know it's confusing, but
So right now we're just looking at the one branch of the,
yes. If you look at the two branches, then there will be a 40 written here. Where is the pointer? Where is the pointer? Yeah, here is the pointer. Yeah, you will write a 40 here, but you will have to put a 2 here because then there will be 2 areas. It's the same thing. I just made my life easy by putting a 20 there. You get my point? I'm not sure whether everyone is understanding this.
Where did you get 50 from?
Where did we get a 50 from? I think 50 I am getting from here, because if I am the force, if I am going right through it, the height available to me is 50, right? So I am flowing right through it, 50. Then I get divided into 2 legs. So height is still 50 for me, right? 50 from here till the bottom. The moment now I'm looking at the left leg, I see this hole. So now there is this chunk on top. There is this chunk here. So I said 50 minus this hole, that is 25. Now I have to multiply with the width. For the width, I am multiplying with the 20. Do you get my point? So now I get a beautiful area right through which the force is flowing. No, confusing? Oh, it's fine. This part I think we can, for now we can skip. Just give me the value. Your book does not talk about this one, by the way, but anyways, for the sake of completeness, let's do it.
40 megapascals.
40. Your book skips this part, but for now, that's fine.
and also it will be compressed, right?
Yes, we are talking about compressed. Okay. Now, here comes the last part, which is very interesting. Let's focus on the portion A, this portion. Now, this portion looks very complicated. What I can do is, I can make a beautiful diagram. I don't have space here, by the way. Okay, now I have the space. So I have this chunk, this chunk, this chunk. So I'm just drawing this again, okay? You can draw it again for yourself. So A. Not the best drawing, by the way. But anyways, I will try my best. Okay. And then we have a beautiful rectangle like this. Then I have another pieces of lines like this. What happened? Okay, and then I have done. And then I will make for A this fellow. Now my drawing is complete. So I'm trying to draw this A portion here. It's rather confusing, but anyways. So I will call it as my A, the whole thing. And what I will do is I will draw it one more time, the pin. So anyone who can please talk about from where did I start talking about the pin? Where is the pin? Where is the pin? You see, this is the pin. Focus on the pin. The pin goes right through it, right? Is it even clear? No, it's not. Let me zoom it in for you. Did you see the pin? Pin goes right through it. That's why the dotted lines. So focus on the pin. Do I have to worry about the pin? Of course, if the structure has to fail, it's not only the rods that you have to worry about. If the pin fails, the structure fails. So you have to worry about the pin as well. That's why from here onwards, we will focus on this pin. Okay. Okay, great. Now, 40 kilonewton. Do you remember that when I was making those yellow lines, I made a line like this. I said the bar is in compression. Then if you remember, let me make the rod. Then there was another rod. Do you remember I made this arrow from last class? And then I told you make another arrow. And I started telling you that this bar is in tension. Now what happens is, if this bar, this fellow is in compression, then what exactly is happening to the pin that is sitting here? Of course, this fellow is putting force on that pin. So I will this time around, by looking at here, will put arrow like this, and I will say 40 kilonewton is acting on the pin. So I will put 40 kilonewton here. Then I will again look at this pin and I will say this poor pin, where is it? It's not visible. Let me zoom in. Where is it? Yeah, now it's visible. Now, this poor pin, force is in this side and these legs are putting load like this on this pin. Are you getting my point? It's a static structure, right? So I will now put 40 kilonewton like this, and I will put 20 kilonewton here, and I will put 20 kilonewton here. Is it clear? 40 acting on the pin. It has a bracket. So of course, that fellow has 20 on it and this fellow has 20. Now you tell me, if this pin has to fail, how would it fail? Think about it. Yeah, who said that? Excellent answer. Shearing, knife, slicing the button. That's how. If it breaks, we will be showing everyone, you know, you see, there are 2 or 3 pieces to this pen. So I will have a shear stress, not the sigma, is equal to V over A. Now, V is for shear force, but if someone had used F here, there is nothing wrong with it. But here comes the most important question of the class. You tell me the value of this V and the value of the area. Think about it. What V should I put? 40 or 20? 40? Okay, let's put a 40. But now you have to tell me the area. Give me the area of the pen quickly. Not in the number, just give me pi d square over 4. Multiply by 2, right? Now it is becoming confusing when this fellow has to break. There are 2 areas, right? One on top. Focus here. It has to break. It can slice from here and slice from here. So now the point of contention is, should I have 2 multiply by cross-sectional area or 1 multiply by cross-sectional area? So let us follow one of the students. He said 2 multiply by pi d square of 4. I will answer both parts of the question. Don't worry. Pi d square. Now you have to give me the answer and then we will do it one more time.
40.7 kilopascals.
40.7 megapascals.
Nice.
40.7, and I will intentionally write it in 10 power 6 pascals equal to 40.7 megapascals. Now do this question one more time. This time we will follow the students who think it should be 20. 20. Okay, what happened here? Why did I put a 40 here? Sorry, 40 into 10 power 3. I think that's why you said kilo. 40 into 10 power 3 Newton divided by, okay, 20 into 10 power 3 N divided by, now tell me the area. So now look at this 20. It is putting a force and it is slicing this fellow, right? So what will be the area? 1 multiplied by pi d square by 4 or 2 multiplied by 1, right? Now if you look at this and this, it's the same thing, no? It's the same thing. So that's why everyone is all right. Who says 40, but there will be two areas, that is correct. Who uses 20 with one area, that is correct.
So we are assuming that the pin is breaking right from the top part or the middle part. Why it can't break from the center portion?
Oh, why it cannot break from the center portion? They will.
Any of the center part.
Huh.
It's like 30 millimeters, so why it
Huh.
can't break?
You're right. This is correct. We will actually work on that as well. So that's the bearing stress. You are right, actually. His question is that we are saying that it will slice from there and there, but at the end of the day, there is a member that is putting like this. So his question is, when the center bar is putting a load like this on the pen, both of them are in contact with each other. Isn't that of worry to us? The answer is yes. We will introduce one more type of the stress that I have not talked about yet. I will call it the bearing stress, and we will solve it. And we will see that may not come out to be of too much concern to us, but that is something we will work on. The problem is not finished. Okay. Is it single shear or double shear? Why don't you talk about that? Double, right? Double shear, why? Because slices right through two portions. Okay. Our online students are encouraged to unmute the mic anytime and ask me questions, please. You can always unmute the mic, please, and ask me questions. Okay. So far, so good. Okay, let's now add one more layer. Let me add one. Yes.
For the force direction in the A part, you show that. Could you zoom, Hocam?
I will zoom. Yeah, this one. A.
Can you go to the yeah, Hocam, when we show it the force direction, do we show towards the B for the 40 kilonewtons because it's compression and because
Oh, okay, got it.
so
Yeah.
forces.
Yeah, so let me just comment on here. His question is that we did say that this bar is in compression, right? So I said that when we found from the last problem, and for those of you who have the pages, A subscript X came out to be positive, right? Can you all double check with anyone who has the notes? From the last problem, A subscript X came out to be positive value. Right? You also have the page. A subscript X,
Yes.
positive, A subscript X. You don't have the pages? You don't have the pages. If anyone has two sets of those pages on one desk and can share with another, and can please, or probably you can share with him, Again, it's entirely up to you. Okay, everyone saw A subscript X came out to be positive. Okay. When we said A subscript X came out to be positive, I am emphasizing in this class, you just put a arrow like this, okay? Like this. And then you go to the right hand side and put an arrow like this to the left. And you say this bar is in compression. His question talks about the fact that now I put an arrow towards the left. So I want to emphasize that you remove the pin, you came up with AX. That means if I don't have the pin, this is how the pin behaves actually. It puts a force on the bar, so the bar undergoes in compression. But at the end of the day, the pin also has to suffer something, right? So if I'm putting a yellow arrow towards the right, I immediately put a green arrow towards the left, that this is what pin is subjected to. So it's a little
Action
confusing.
reaction.
Action and reaction. That's why. So everything starts from the last problem. Do remember, you got the AX positive. We were happy. You got the CX negative, I think. Just double check. CX was negative.
Yes.
CX was negative, right? So CX was negative and CY was positive.
Yes.
Okay, CX was negative and CY was positive. So I asked you, please make a beautiful arrow like this. Then I said, flip it and put an arrow like this. And I said that this bar is intentional. So I keep repeating it so you remember where did all this discussion started from. Okay, let's finish the problem, the last two parts. Now focus on the B. Focus on the B. Now look at the B. Where is the B? Yeah, there is the B. So do you see that the B actually has a pin? How many see the pin? Where is the pin? Where is the pointer? Yeah, here is the pointer. This is the pin. Let me just ruin the diagram. A beautiful pin goes right through it. Okay, let's do a Control Z. Now the problem is becoming complicated. I am focusing on the pin. When I'm focusing on the pin, how many portions the pin is subjected to? Number one, look at here. This portion, load is acting, right? Okay, done. Then, oh, the problem is complicated, no? Let's look at, look at from here, please. Where is it? Okay, let me draw a yellow arrow so that all of us are on the same page, okay? Let me draw a green arrow. So the green is for this one. I hope I'm not making a mistake. You also let me know if I am. Green, green. And let's make a red for the bar. Let's make a red for the bar. Done? Are you getting me? So it's two different views of the same problem. Good. So now I will do a Control Z. Okay. Let's stop for a few seconds. Is it clear or not? There are the same portions. Now let's make a beautiful pin. So I will make a pin now. Give me 1 second, please. I will again make a drawing. I will zoom in. And now I will start with a pin. And now you will tell me whether it makes sense or not. Let's quickly do it. So this is the pin. Beautiful. Nice and easy. We have a pin. Done. Now, this pin, I will call that this is B. So that's B. That's nice. Then I will make different little portions of the pin. That's one. Then let me make another. That's two. Then let me make another. That's three. Oh, that's not good. 1, 2, 3. 1, 2, 3. 1, 2, 3. There is a 4, there is a 5. There is a 4, and then there is a 5. And then I will just use a razor. Just bear with me. I know it's complicated, but trust me, the first 2 sessions are the most complicated. After that, you will have a feel of the subject. I am intentionally making such a complicated problem, so you have an idea. Yes.
No, right now we just calculate stress in bars and pins.
Yes.
We are not looking for they will be in failure or.
No, we are not. Because unless I did not even tell you whether it's steel or not, whether it's aluminum or not. What exactly is the material? If I haven't specified the material, you cannot infer anything. Right now, I'm just telling you, calculate the stresses. If I tell you information about the material, that's when we start piling up everything. So right now, we are just on the very introductory part. Okay, so what I'm doing is I have divided this pin. Now let's play with it. For those of you who are saying we are not getting how did you make so many portions, I will help you by saying, where is the 20 kilonewton arrow? Where is the 20 kilonewton arrow? 20. Okay, let's make the 20. So wait, the 15 is here. Please give me 1 minute. 15 is here. 15 kilonewton. Okay, can you please identify where is the 15 from the figure? Then make another 15 right at the edge. So we have another 15 here. No? Yes, please. Yes. Someone raised hands? No? Okay.
30 kilonewton divided into 2.
Yes, right. Because look at here. This is 30. It's 15 here and 15 here. So that's why I am just looking at the pen. Now, what about the, why don't you tell me, what about the, oh, where is it? 20. Where is the 20?
The 40 is divided into 2.
40 is divided into 2 because if you remember, which bar had 40? I think this one had 40, right?
Yeah.
Okay, if this bar had 40, then now I will put a beautiful 20 here. And if you look at, we have 2 portions, so I will put a beautiful 20 here. I know it's confusing, but we have to deal with it. So I think I will put a horizontal arrow here. Correct or not? Please. Okay, 20. Okay, what about 50? Why don't you do it yourself? Where is the 50? We have students who are sitting right at the back. I will zoom it in. No, it's not visible. Sorry. Where is the 50?
At the center with a 30 or 60 degree angle.
At the center with an angle. So I will put like this. Somewhere like this. And I will put an angle. Is it clear or not? Yes, no, confusing? Yes? Does it make sense? Yes, little bit? Okay, good. You have to realize that this is this is as hard as it can get for an introductory problem. But my point was, let's make a comprehensive problem so you have an idea about the pins and everything. Okay, everyone done? Now let's do the numbering. So I have a nice and beautiful E. Oh, where is it? E patch. No, let's actually use this line as a reference for E. Then let's use this blue line as, oh, what happened? F. Then use this line purple as a G. And then use this, where is green line, as an H. Yes. Now you all help me with the lobes. So I will make a, for the B, this whole pin is the B. I will make a B. And now let's do this together. We have 50 kilonewton like this. Nice and easy. We will go for a break, by the way. And then we have 40 kilonewton here. Oh. And then we have 30 kilonewton here. I'm intentionally making the side view now. So we have done. Just finish the problem, and then we will have a break.
John,
Yes.
in that case, it will be complicated, right? Because in E part, the 15 kilonewtons acting and also 20 kilonewtons acting, right?
Okay.
So in E part.
Okay. So in statics, I'm sure you have completed everything. In statics, they did tell you, right? If you have a bar, there are loads that are acting. Then they used to tell you to cut and throw the chunk away and start looking from one side. It does ring bell, right? Everyone. Okay. So this is what exactly we will do. This is a pin for me. Loads are acting. I will keep slicing it and I will keep throwing the chunks away from the right hand side. So in this way, step by step, I will keep marching along. So follow me. I will answer your question right away and all of you have this task. Quickly do it. Why don't you all tell me what is the shear stress? Where is E? So please, everyone, you see this blue line is the E line, okay? Let me highlight it for you. This blue line is the E line. Why don't you tell me what is shear stress at E? No, 35. No. If I have to, if this is the line of interest for me, I will make my life easy. I will use a knife, I will cut and I will throw the whole chunk away. So I will, where is the pointer? Yeah, I will throw this chunk away and I have this little fellow to play with. So you throw the whole thing away. Where is Control Z? So what will be the force that is left? 15, right? Are you following me? Done. Done. It's done. Divided by area. What is the dia? 25. Yes, I think 25. So let's do it. Oh, where is pointer? I'm still finding the pointer actually. Okay, pi 4, 25 by 1000. And you can give me the final value, please. 30.6 and units. So it's 30.5 into 10 power 6 pascals. And I will say 30.5 megapascals. Boom. As easy as it is. Nothing. Yes. Yes.
So we're thinking like limit stuff, right? We go towards from left to right.
We can go from right to left as well.
And we will get same answer.
100%. But if I ask you right now, go from right to left, it's just like making life complicated. If you go from right to left, there's just so many things to take care of. Okay, quick question. You have got the tau E. Why don't you tell me tau F now? You do it yourself, please.
We should consider all of the forces, right? So 15 will be counted in.
Oh, of course. If you're talking about F, I'm talking about, let me help you with the highlighting of the section. Everyone, you see this? So I'm using the knife to cut this. So this means, as one of the students indicated, now I have to worry about 20 plus 15. So it's a little hard, by the way.
So we need to consider.
Yes. Oh, wow. How did you figure it out? Good. Good. We have to be careful. Yes. That was the right answer. Wow. Oh, what happened? Oh, so it's VF by area, and V is now complicated. So as one of the students indicated, we will have to use, the whole triangle rules. I will just tell you how did he figure it out. This is the section F that I see. We know that when I'm looking from here, there is definitely a nice and beautiful 20 kilonewton that is acting. And I also know that there is a 15 kilonewton that is acting. Now, I know your concern. You're saying that 15 is here and 20 is a little back. But at the end of the day, when you cut and you look, you are seeing both of them, right? 20 is in the back and 15 is in the front. That's fine. So what will be the answer?
50.9 megapascal.
Oh, you have to tell me the V first.
25.
25, right?
Yes.
Where is it? Oh, I don't have space, by the way. That's not good. Oh. No, you can ask me what happened. What happened? So should I explain the 20 and 15? 20 and 15, right? So I'm looking at it. So for me, it's now 25. Okay, where is it? 25, as one of the students said, with a kilo. Boom. Area. Okay, I think you can all do it. It's pi d square by 4. Pi d square by 4. What was the final answer?
50.9.
50.9 megapascals. Oh, where is the answer? I don't have the answer. 50.9. Nice and easy. Problem is done. Now, before we go for a quick break, why don't you all help me with this? What will be the shear stress G?
We have to find the angle first.
No.
But then can we say that it's 50 and it's 25 for subtract? It will become.
No, actually, the answer is way easier than what you all are anticipating. It's very easy. Right. It's the same, because shear stress at F and shear stress at G. Just flip the problem. Start looking from there. It's the same thing. So actually, it's this. Where is the point? It's the same thing. I will write it is equal to. It's the same thing. And I will not stop here. What about tau E? I'm sorry, tau H. Agreed?
Yeah.
You can have a quick look again. Why tau E and tau H are the same? You flip the problem. Now start going from there and slice is the same thing. So just for the sake of completeness, we had one of the students who said about that not internet, Pythagoras. So for the sake of completeness, I will put F and I will put 20 kilonewton and I will put 15 kilonewton. And as one of the students said, before going to the break, why don't we use the triangle and we have 25 as one of the students helped us. Okay, so we can go for a quick break. 11:43, we are meeting again. Pi r square and pi d square by 4 is the same thing actually.
So this is actually pi r square, right?
Exactly. So
So that's what I was confused.
no.
I thought that this area was curved area.
No. Perimeter, no. This is the cross section area. So I call it, I say pi d square by 4. You say pi r square, but both of us are saying the same thing. So you do
But
it.
this is an r,
This is a D. This is a dia.
which is what's actually.
Dia, 20 millimeter. You see, this is a D.
So if I wanted to pi r
I
square,
will.
that's at the bottom.
Pi d square by 4 pi r square. Both give me the same thing. So if you do instead of r, radius is d by 2. It will give you pi d.
So go to square and d square.
It's the same.
That goes into the power of that.
It's the same thing.
Okay, sorry.
So no. You can keep on going.
And then, so this is positive, first I was curious. I was actually confused with this area as well. Like at pin B, this is the area we are considering. So which point of view?
Yes, okay.
Can we use?
I will. So what happens is that right now I'm looking at this circular rod, right? So for this circular rod, I was super clear that if I have to find the stress, it will be force per
Which is-
unit area.
Which is what applying.
Exactly.
So it's clear.
Pretty clear.
Yeah.
But the problem is that now I'm concerned that this rod actually has if you look at the side view, it's a flat, the rod becomes very flat here. It becomes, you can see, it becomes like this flat piece here, this rod. So I'm scared that this rod, instead of breaking from here, might end up breaking right through this, the portion where the dia is there. If you can highlight it. The thin portion, the thin portion. I'm scared that it will break right from here because you can see.
The rectangular piece.
Yes, it has become flat, but I'm scared that it will break right from here and here because it does make sense because you can see that the hole is so big and the portion has become so thin.
Oh, we're talking about little pieces.
Yes.
On both sides. Like
Yes,
very little.
exactly. If
Wow.
it has to break, it might end up breaking here. So my intention is, why don't I find the stress right at this portion and right at this portion? In order
On
for
both
me,
sides.
on both sides.
Mm.
So in order for me to find the stress on both of these little fellows, because right now the area was big and I was happy, but now I am scared. So what I can do is I need to find the area of this little chunk and this little chunk. So everything I started doing from here onwards, I was actually trying to find the area.
Okay, so at this part, we calculated the area like this.
Okay, I will tell you how.
40 minus
Uh-huh.
25. is-
Yes.
So 40 is this portion, the whole. rectangle.
The big thing, but the moment I remove,
I don't need that.
25 is the whole, the
Oh, the
diameter,
diameter of the hole,
the diameter of the pin or subsequently the diameter of the hole.
Okay.
So the moment I subtract the 25 from the 40,
Mhm.
I'm left with this chunk plus this chunk.
Yeah.
Now, in order to find the area, I need the second dimension, that is the depth.
Mm.
And in order to see the depth or the thickness, I immediately realize that thickness, I suppose, is 20. So it will be 40
can't I just do 14 minus 20, which will give me both those little pieces? Because this is 20
The problem is,
and this is 40.
the big problem is that this whole has absolutely nothing to do with this. So that's why I did a 40 minus 25. And it
Multiplied by 20.
the 20 for me is the thickness, because the top view tells me that this in the thickness or in the z dimension, it is
It's the height, let's say. all of that.
thickness or depth.
Yeah, okay. So that's when you apply.
That's how the force
Yeah,
flows
yeah.
through that little chunk.
Okay. Okay, I get it. And then one more thing.
Yes, please.
This, I think, I thought of myself, why is the areas are reversed? Because at pin at A, we said that there is here, 220 kilonewtons and then 140 kilonewtons, because there are two pieces that are connected here, and there's only one.
Okay, I will tell you.
And so my question is, so there is 140 kilonewtons. So we have to have one area that is being applied. Why do we multiply by two?
Yes,
Is that
I
okay?
will. You show me the picture. So for example, this is the 40. The point is that this 40 is encountering two cross-sectional areas. You cannot say this is a 40, so I will have a 40 here and a 40 here. No. If this rod has 40, if it is applying even a load of 40, then you see this bracket has two legs.
Yes, yes.
So each leg will actually come up with a 20 and 20.
I'm saying those 20
Huh.
kilonewtons divided by 2.
No, 20,
I mean 40, sorry. 40 divided by 2, because it's applying both ways. I get that.
that's 20.
That's the
But then that 20, this 20 is only looking at this cross-sectional area only. So I will have to do a 20 divided by this only. But if I do a 40, this 40 is actually looking at two cross-sectional areas. So if I use the 40, I will have to use this A plus this A. But if I have to use this 20, I have to use only one A. So that's why it's
So it's
so
not actually the places being applied to.
exactly the place that you are
I'm not
applying.
considering the area that is the force is being applied to.
I am considering the force that is applied on the area. This is the force, and this is the area. This is the force, this is the area. You see this area? The place where the pin can, no. This is the pin. This is a pin. This is the load. It can slice right from here. This is the portion where it can slice, because this is the bracket. This is a pin. This bracket can slice the pin right from here. So it will be a force divided by this area. 20 divided by this one area. But this is the force, and it's looking at the area.
So I guess I consider because of the shear stress.
Yes.
Shear for now, it's
Probably. Yeah, next class I will in the office I will definitely, I will print and I will forward. This time around, I think I brought less copies. If you can please share for now.
Thank you so very much.
Thank you. Okay, where are we?
Draw the loads for the shear forces for the from the E and EF. How can we draw? Like in statics, we draw shear forces when we go towards the.
Okay. Okay, I will do it. Yes, let's do it. Let's do it. You are right. So let me now, yes, I actually understand the question. I really want to get rid of this paint now, but this is easy for me. So let me now go back to whiteboard. I hope our online students can see the whiteboard. So it's easy for me. So I will actually use what you just told me, the statics. So that's my E. And this is the V. I will also show the diagram to you. So that's the V equal to 15 kilonewton. Then I will say this load is 15. That's why I put a shear. So shear stress is equal to 15 kilonewton divided by pi 25/2 square millimeter square. So let me show you the diagram, otherwise it's very confusing. So 6, 5, 4, 3, 2, 1. So where is the shear stress E? So this is the E. I need to explain this. This is the E. Look from here. Stand here from the side and now look at the pin. Now, if you look at the pin, this pin is not appearing to you as circular anymore, right? You're looking at just a rectangular chunk. Are you following me? This is circle, right? Cylindrical. What does it appear to you? Nothing. From here, from the side view. If I have to just see, for me, just this. It's just a rectangular chunk, right? So from the side view, if I see this orange chunk, it will look to me as a rectangle. So that's why I will make a rectangle like that. And I'm looking from here. So I will go back one more time. Now I am seeing a 15 kilonewton that is hanging from here. And I can see that right on this section, there will be a shear of 15. So just because he said the way we used to do in statics, I said 15 is hanging, subsequent 15, shear stress is equal to 15 divided by the area. And for those of you who are wondering, how did you come up with the circular area when it is a rectangular? This is the circle. You see, because from here, it's still a circular rod, right? So this is how you do, if you really want to do it using strictly the way you used to imagine in the statics. But anyways, I hope it became clearer instead of confusing. Okay, so let us go back one last time. I will continue with the problem. The problem is not finished.
No.
Yes.
So after the E, what will be the force distribution like? It will be 25, right?
Oh, for E. Oh, after E for the F?
From E to the F.
For the F. So let's talk about F. Okay. Let's talk about F. For the F, I will have a 15. I have a 20. So for the F, I have 25. I still remember I did that. This is the VF I wrote, and then I wrote a 25. So you are absolutely right.
So if you show the drawing graph, this is the x-axis and this is y-axis, the 15.
It will be at an
after that,
angle.
It will be 25.
But it will be at an angle. That's why I avoid making the diagram out of it.
Okay.
Okay, everyone, let's continue, I think. So we are done. So let's continue if it's clear. Let me make the bracket for you and let's finish the discussion. Okay, please bear with me. Okay, bearing stress. This will address your question. One of the students who asked the question. This one is normal stress. This one is shear stress. Correct? Normal stress, you remember? Normal stress is this one or this one. If I pull it, that's normal stress. I'm inducing a normal stress. Shear stress. Okay, so this fellow, if I really want to subject it to shearing, I will twist it. Or if you have a textbook in front of you, you just do this. So the pages will change an angle. That's a shearing stress. Or if I have a knife and I cut it right through it, But bearing stress is something that you haven't heard till now. So this is what bearing stress is. This is one surface. This is a different object. If I am putting a load, both of them, this and this, are being subjected to bearing stress. Bearing, B-E-A-R-I-N-G. So this is bearing stress. Both of them are in contact. They are bearing. So different materials, it is subjected to bearing stress, both of them. So the question is, why it is so important to us? So I will explain this by going back one more time. Look, let me zoom it in for you. You remember this? Right? So we kept on saying, so focus on here. Where is it? The pointer. Yeah. Focus here. You remember we said that the bar, this one, is subjected to a, which one? Compress. The load was like this on this bar, right? Right? Compressor. And then we draw arrows like this. Then we said on the pin, it will put a load like this, right? And then we said this pin will can break on two portions. It can break from here and it can break for here, right? But then one of the students said, why aren't we concerned with this bar putting a load directly on this pin? So it's contact. That's the bearing stress right now we are talking about. It makes sense?
When does it fail, the bearing stress?
When does it
Fail.
No. So once I calculate the bearing stress, I will get a value. Then all these values I am getting, I will have to compare it with the structural limit that I haven't even talked about, because this, if it's made with aluminium, will have a different response. With the steel, it will have a different response. With a glass, it will have a different response. So we haven't even got into that. For now, I'm just looking at the values and I'm saying, oh, this value is big. It's important for me. Now I will need those pages actually. So let us do one quick bearing. Where is it? Yeah, then I will give these pages to you at the end. Everyone, let's do it. So we have bearing stress. Let's do a bearing. Oh, bearing stress. So I will have a now quick comment. Bearing stress where? Bearing stress in the pin or bearing stress in the bracket? You have to be careful. There are two portions. This is a bracket. Focus here, please. And then here, both of them are bracket. So for our online students, bracket. You see this bracket? This is one portion. And then you have a pin. Right. So we have pin and bracket. Wait, the story doesn't end here. The pin meets with the bracket. The pin meets with the bracket. Is that it? No. The pin meets with the member, right? Are you following me? The pin meets with the member and the pin also meets with the two legs of the bracket. So pin, member, bracket. Between the pin and the bracket, then between the pin and the member. When he asked the question, he was focusing on the pin and the bracket. So now we have two different questions. Oh, that's one big question, right? Okay, let's do it. So member, determine the nominal bearing stress at A in member AB. So let me write down the English for you. Determine the nominal bearing. Oh, what happened? Determine the nominal bearing stress the nominal bearing stress at A, where is the paint? Oh, what happened? Okay, I think, okay. Determine the nominal bearing stress at A, in member AB. Okay, so let's do it. The answer is stress equal to, we have force divided by area, right? Okay, what is the force? What is the force? 40, correct? Determine the nominal bearing stress at A in member, right? Member AB. So its member has 40 divided by, what is the area? This is difficult. What is the area? Think about it. Of course, I have to explain this portion. So what happens is, first I will write the answer and then I will do the explanation part. So it will be, if I have to look at this time around, I will have to look at the rectangular window. I know you will be like, what on earth is happening? Why are you making this is the portion, so I have to, oh, what happened? Like this. So you see this, I have to look at even when it is circular, I have to look at the rectangular window. Even when the pin is circular, I have to look at the rectangular window. So it will be thickness multiplied by dia, which is 40 kilonewton, divided by, what is the T?
30 times.
That is 30. So for students who are saying how did we figure? How did anyone figure? That's 30. That's 30 multiplied by. Now the pin is 25 millimeter in dia. So that's a 25. So you can all find the answers. Now I have to come up with an explanation. 53.3 megapascals. So bearing stress apparently is confusing. Okay, answer to it. This is the answer, 54321. So what happens is that if I have this object and I have this object, and then I have this object, and then if I have this object, and now I have a nice and beautiful pin, let's say. So let me make a bracket for you. Then we will talk about it. Trust me, it's very easy. It's the first time it looks complicated. It's not. So you will understand why did I make the area in such a funny way. Now here comes a nice and beautiful pin that is sitting on it, okay? So this pin rests over it, okay? Now just imagine if this pin has to be in contact with this fellow, how that force is being applied. Arrow, arrow, arrow. Then will be another arrow, another arrow, another arrow, right? So far, so good. The point is that if you look at the right arrow and the left arrow, then the right and the left, they cancel. This right and left cancel. So all that you have left with is something that is being directed directly towards it. So I will put another arrow like this, saying that the left component just cancels with the right component. Are you getting my point? So that's why at the end of the day, when the right and the left, they cancel, the area that you are really worried about is this area that is projected. So that's why you can't care less about the circular portion and you are only looking for the projected area for bearing stress. Yes. We use the projected area. That's why. So probably for the sake of completeness, I will say we have, let's say this is the load. Then we have on this pin, and then we have, I think the arrows are like this. So okay, let's go back for now and let's see whether what we did makes sense or not. So is this clear or not? No. Okay, why don't you do the next part? So we will see whether everyone is clear or not, because till now I'm not sure whether you actually got that. So the next part is determine the bearing stress in the bracket at A. Bearing stress in the bracket at A. Please do it.
So for all the answers, should we not convert the millimeters into meters?
We are. I am converting. I am converting. So here probably I did not mention, but if you see many times I'm doing it divided by 1000.
Okay.
So our online students can do it themselves as well. So pin is touching the bracket at two portions, right? And it's touching like this. So I have two chunks that I have to take care of. So I don't have the answer. Within a couple of minutes, I will. In fact, I will take the last page from you. And, one page. Are you using this one?
No, not right.
So Bijan, we
Yeah.
can share it.
Can you?
Yeah.
I will. I really appreciate, please. Yeah. What is the answer?
I told you to.
You figured it out. Yes. You are getting this point, right? The bearing? No, yes. Did you understand the bearing stress part? So for example, yeah, this one. So this is the bearing stress we are talking about. Bearing stress in the bracket. So let us go back, see the figure. There's the bracket and this, the bearing stress between the pin and the bracket. Now this pin is touching this bracket here and here. So you have to actually find the area. So it will be the thickness multiplied by the depth. So if you go back, that's why it says there is a 50 multiplied by 25. And why 50? I think he also explains here. Yeah, 50 yeah, because it's 2 multiplied by 25. So if you go back, see this little thickness and then this little thickness, both of them are 25. So it's 2 multiplied by 25, and then we multiply this with the other dimension, which is the 25. So it's looking at that. Projected area.
Yeah, otherwise then
Better.
and the.
So it will be on the pages too, right?
Yeah.
For
one page.
Next time. None of you have any pages? No. Okay, I have counted the students, so next time I will break. Okay. Okay, I'm not sure whether everyone got it. So let me do it for you together. Now we have to find the bearing stress between the pin and the bracket. So this is the pin. This is the bracket. How should I make it? That's one complicated drawing. Right. It goes right through it. And then it goes right through it. So what is the dia? The dia is 25 millimeter. So just imagine it. This is the depth. And then I have to see this dimension, which is again, I think 25, right? So it will be this 25 multiplied by this 25. So I have this beautiful portion. Then I have this one as well, right? Because it is in, the pin is in contact with the bracket here as well. So it will be 2 multiplied by 25 multiplied by 25. That's the area. I'm not even sure whether it was clear. Let me make one last attempt in making a better diagram. Okay. Let me make one last attempt. So we have stress bearing in the bracket and the pin, between the bracket and the pin. So it is equal to force divided by TD, which is equal to 40 kilonewton divided by 50 multiplied by 25 millimeter, which is actually 2 multiplied by 25 multiplied by 25, which is equal to 32 mega. So there are 2 of these brackets. Yes. There are two of these brackets.
When I calculate hocam,
I just 1 second. I have finally figured it out how to explain to all of you because I was struggling with the 3D drawing. Sorry, just give me 1 second. So it's this thickness, sorry, this dia multiply by this dimension. That will give you this area finally. Oh, I'm so happy right now. Then this dimension multiply by this dimension. It will give you this. Is this clear to you? Now, right? Now this is clear. Area. Now it's clear? No? Yes. Okay. Yes.
hocam, when I calculate it, I do like 20 kilonewton divided by 25 times 25.
Yes. Good.
Then
Very good.
Multiplied with 2, hocam,
Oh,
I said.
But
Because
then
of-
the answer changes.
Yes, it will be like 2 times of the answer.
No. What you just said few seconds back was correct. What you did is you said it's very good. You said it is p by 2 divided by 25 multiplied by 25, right? Very good.
Can you change the color?
Oh, this is definitely not visible. Okay, thanks for pointing out. This is not visible. Sorry. Thank you. So it will be, what did you say? P by 2 over 25 by 1000 multiplied by 25. Correct? So this is correct because half of the load is being transferred to the top bracket, the half to the lower bracket. So the half load and the half of that contact with the pin. That's correct. But don't multiply with the 2. Done? Clear? Feeling better? Okay. So, okay, great. That takes us to okay, everyone. On that note, how much time we have? Okay, so let's quickly finish everything by saying this is what we have done till now. Okay, few announcements. We are using Bear Johnston textbook. Please make a remark. Bear Johnston. BEERJONSTON. Okay, now just to be a little up to date, I have 8th edition with me. I have also 7th, 6th, 5th, all of them. As long as you have 6th edition onwards, it's fantastic. If you have 5th edition, I think that's fine as well.
Do we have a PDF version?
Oh yeah, it's available online. Lots and lots of pirated versions are online.
Hocam, I bought the 7th edition.
Great, good. Oh yeah, just one remark. Now, I just saw that you have SI written on it, right?
Yes.
That's fine.
Okay.
But just remember that in this class, I will keep on throwing British system units. Now, it's not to confuse you. It's just to give you a very, very basic familiarity. So at the end of the semester, the pound force, pound mass, inches, you will not remain unfamiliar with that. So if you can get hold of a general textbook, that's better. If you have already got hold of a printed SI edition, that's fine. Don't worry. I will provide you with a soft copy.
What is the books in the mechanics of materials, right?
Yeah, can you just please read the name and show it for all of us? I appreciate. That's the mechanics of materials. Yes, thank you. Okay. Okay, and everyone, life is good. I will make a book and stuff folder on the Google Drive. Please give me time till the weekend. posting lectures and everything, you have to give me time till weekend. And in that, I will also post some reference books for you. So, okay, everyone. Let me make this for you. It's very confusing because I first made this. Please bear with me.
What is this for?
Sorry, this diagram? This one? I'm just talking about a few more things. The textbook part is over. Okay, so we said that normal stress is equal to force per unit area. So this is the force that someone is applying. Okay. And they are holding it from here. If they are holding it, then there will be a reaction equal to this applied load. Or you can say someone is also applying the same load. Either way, it will still be an F here. Then we said, I have a beautiful cylinder. One more time. And then I said, I am applying a load like this. So it is. Then I said, I am applying exactly the same load like this. And I said, the shear stress is equal to P divided by A. Are you with me? Right. Then I said, I have a beautiful steel plate, nice and beautiful. And on that steel plate, I'm actually putting a circular rod. Right. And I'm putting a load on this circular rod. Right. And this is the load. And few students said, what is happening right at the intersection? And I said, you know what? This is what is happening at the intersection. So I said, this is stress B equal to F over A. Let's say this is your F over A, P over A, whatever. This is the bearing stress. Average bearing stress. There is one more student who said there is a steel column and there is another plate at the bottom. They are two different fellows. Can you just tell us what kind of stress at the contact? Bearing stress. So I'm just summarizing all the fancy things we have done in this class. So far, so good. Okay. Now just to finish our today's class, I will finish it on one thing. And it's very hard to make 3D drawings, I swear. This is a line, and then, okay, let me, okay. And then we have another of this. And then we have, so we are putting a slice right through this chunk. And right now you're wondering, why are we putting a slice right through it? I think I have to continue in the next class. It's very hard. Three-dimensional drawing. Okay, I think I've done it. Okay, and from here, okay, just bear with me, please. So what I'm trying to do here is, I'm trying to okay. This has become one complicated figure. Okay. You have to bear with me. I think we are going to the next class now. But I will give one last try, and otherwise I will finish it. Oh, come on. Come on. Come on, come on. Yes, as easy as it was. I'm not sure why I was trying to make it very complicated. Just one little leg here. Everyone is understanding what I did, right? So this is a big box, and right through a plate I'm putting it. Okay, what I'm trying to do quickly. I have this stick, right? You hold one end, I hold another, and we try to pull it, right? We try to pull it. What happens is, when you pull a wooden stick, let's say like this, and I'm pulling it, you never have flat sections when you pull a stick. When you break it, it breaks at an angle. And let's say this part is like this, and the other side that got, let's say this side has this edge, a beautiful edge like this. The other side will have this cone from which it breaks away. Now this angle is approximately 45. Now I'm not saying that every time you will have a 45. Here's the big question. When I'm pulling this stick like this, why does it break at 45? Why doesn't it break at a flat section like this? Similarly, if you have, let's say, what example should I give? So for example, if there is a lot of load that you're giving again to some column or some wooden stick, if it collapses like this. If you keep putting a huge load, it will not collapse at like a flat edge. It will collapse at an angle, and this angle will be again 45, nearly 45, not exactly 45, probably 40. What I'm trying to say here is that you are applying a load like this or a load like this, but there are lots and lots of sections inside this object that are more vulnerable than the other sections. So from the next class, what we will do is We will make a slice right through it. I will tell you that I am putting a load of some 20 Newton or whatever here, and I am putting another load here. And we will see that on one particular section, what kind of normal stresses and shearing stresses we will have. Okay, so that's what I was trying to do, but it took a lot of time just to make this drawing. We still have 3 minutes. But anyways, we can continue this next time. Oh, okay. Yes. You can have this. No, this is yours. This is yours. Okay. Hello, Saad. How are you? Saf, sorry. I will, if you're free right now, I can print it right now. It's in Bear Johnston textbook as well. Okay, you can have it. Okay, on next. I will add you. Send me an email right now. I will add you.
Also, I have a question about bearing stress. So when we're dealing with bearing stress, we didn't looking at the areas, curves or something.
Yes,
kind of
no, we did
We're just
not, right?
looking at the projection and
That's so funny, right? Yeah, exactly. We just, because we said, because the force distribution is like this. So this arrow cancels the right, cancels with the left, this cancels with the left. So the resultant force is acting like this.
so
If the
we're just
resultant,
looking at projection.
if the resultant force is acting like straight like this, then there is no point of the curved area, right? Because I completely said the right cancels with the left, the right cancels with the left, and I took everything, and there is just one giant vector that is acting like this. So what exactly is sitting right for that giant vector? There is just this projected area.
And also, Hocam, I have a question about this part. You said that Hocam, you didn't multiply with 2, but when I doing the calculation, I just focus on this part in bracket. And if you want to in that case, so I will get bracket.
Oh, got it. So once you get the stress for this, then you multiply with the 2.
Oh yeah, just this part, and it says bracket A, so I need to
Multiply
look
with the
at,
2.
multiply
No.
with 2. Oh, okay.
No.
Attendance.
No attendance.
So you're just looking, thinking that 40 and divide by 2, like.
You know what? I will say like this. We don't just add the stresses of the 2 components. This part has stress. The other part also exhibits the same stress. But I don't just add this value. I don't just multiply with the 2 because there are 2 of these. So for example, just imagine if I have 2 of these fellows that are holding on to some force and they are stressed. If I end up finding it stress and I say this other one is subjected to similar conditions, same conditions. Oh yeah, the other one is also having the same stress. It's not this multiplied by 2.
Okay,
You
okay.
get my point?
Okay, I get it.
It's
You're
more
just
like
looking just one of them and
it's more like
same stress.
it's not the right example, but it's more like there are 2 partitions to the room. This room has 25 degrees Celsius. This room has 25. I remove the partition. The whole room has 25. I just don't add 25. It's
Okay.
not the same example,
I get
but
it.
that's the mistake you are making.
Okay, Hocam, I get it right now. Thank you so much.
Okay, thanks for
Thank you very
lending me
much.
this during the class. Thank you. Bye bye.
Thanks so much, Hüseyin. Have a very nice day.
Oh, thank you.